Okay, so today we'll start a new chapter, and this chapter is an important chapter. And this chapter is DC motors or DC machines. We will see what is the difference between machines and motors. And in this chapter, we'll start by an introduction, then the construction and theory of operation of DC machines, equivalent circuit and electromechanical relations, the different types of DC machines, torque speed characteristic, which is an important topic, DC series machines or DC series motors and their applications, how we can do power flow, and usually I cover the power flow in this part in the types of DC machines, and we will solve some examples before moving to speed control and applications of DC motors. So these are the topics that we are going to cover in DC machines. So let's start by an introduction to give you an idea about DC machines. So let's start by an introduction. In this introduction, we need to learn two actions. We need to learn the motor action and we need to learn the generator action. So let's start by motor action. So hopefully after this introduction, we can write down the story of motor operation and the story of generator operation. So let's start by motor action. So what is motor action? Motor action is to generate force. You need three elements, okay? So the equation for forces that we learned is that the force equal to BIL sine theta, and theta is the angle between B and I. So this equation is the equation that relates the force to the components, and as we can see, there are three basic components. So we need flux density, we need a current, and we need a length for the wire. So we need to have flux density, we need a wire or a conductor, and we need to supply a current to this conductor. If we manage to have a wire subjected to flux and carries current I, this wire will produce force F. And this is how we can produce a force. So assuming this is the plane we have. So assume that we have a wire. This is a wire or a conducting material. And this wire is subjected to flux, which is vertical flux perpendicular to the plane we have. So this is flux density B. So we have two components. We have a wire, we have a flux density, and this flux density or this flux B can be from an electric or permanent magnet. So we can have the flux from a permanent or electric magnet. So we can have a flux from an electric or permanent magnet. A permanent magnet is magnetic material that produce flux without a source. An electric magnet is just a core and we have a coil around it to be able to generate flux. So we learned in the magnetic circuits how we can establish a flux with certain flux density B. And this flux density is applied to a wire or a conducting material. And to produce the force, we need our third variable and or our third element, which is the current I. So to get this current I, we will connect a battery V. So we need an external source. So this external source will supply the current I into the wire. So we have a current I going inside the wire. If we have these three components, which is the flux density, the supply, and the wire, we are generating a force. And to get the direction of this force, we will use the left hand rule. Okay, so the direction of induced force, and we can call it as F electric because this force is induced due to the electric effect. So the direction of the induced force follows the left hand rule. So what is the left hand rule? Just I will bring my left hand. So if this is your left hand, you will receive the flux into your hand. So the flux should be received into your hand. This is the flux. So the flux should go into your hand. Your fingers should be pointing to the direction of the current. Your thumb will point to the direction of the force. And this is the left hand rule. This is the left hand rule. So if we apply this left hand rule here, if we apply the left hand rule here, so the flux is coming into the hand, the current is going in this direction, so the force will be in this direction. So here is the current, the flux is going down, so the force will be going in this direction. So this is the direction of F induced according to the left hand rule. Okay, so just let's rotate the hand so you can see it. Okay, so the current is going in this direction. This direction is the force, and the flux is received into your hand. So the flux is going inside your hand or perpendicular to your hand. So you are receiving the flux into your hand. This is the direction of the current, so the force will be in this direction. So this is called the left hand rule. So this is the left hand rule. So according to the left hand rule, we are inducing or we are generating this electric force, F electric. And this F electric will move the wire, this wire to the left. So if you have a flux vertical and you have a horizontal wire, this is a wire and this is flux, and you injected current into this direction, I, the wire will move to the left. If it changes the direction of the current, so if the current is going in this direction, this is I, so the wire will move to the right. So you can change the direction of movement by changing the direction of the current or by changing the direction of the flux according to the left hand rule. So if we put the left hand rule here, so if you receive the flux into your hand, this is the flux, and the current is going in this direction, I, the force will be in this direction. This is the force, so you are moving to the right. Or this is the case that you are moving to the left. Just I will show you a video to prove that this is the main idea for motors. So let's bring this video here to see the basic idea for motors. So what we have here, we have the silver here is the battery, the magnet. Then we have a battery and we have a wire. Okay, so we have the wire, the battery will circulate the current, and the magnet, which is the silver part, we had down or below the battery. And this is how you can get a Valentine Day gift for less than $2. So as you can see, if you have a flux wire and you injected current through the wire, there will be a force, and this force will move your wire. Okay, so let's add another page here. Here just I will explain explanation of the left hand rule. Okay, so how they came up with the left hand rule. Okay, so let's take what is happening for left hand rule. So assume this is a wire here, and around this wire you have flux. So there is flux lines on the right side of the wire, and there is a flux lines on the left hand side of the wires. And these flux lines are going vertical. So you have flux lines vertical, and then in between them you added your wire. So some of these wires or these flux lines are on the left side, and some of these are on the right side. Okay, now this is the case. So this is the case without current. Okay, so this is the case without current. So as you can see that the flux will be uniformly distributed, and the flux lines will be vertical lines. Okay, now let's see what will happen once we circulate current inside the wire. Now if we start to circulate current inside the wire, current I, this current will start to create flux lines around the wire. And to find the direction of these flux lines, you will hold the wire by your right hand. So the flux lines will be going around in circles. Okay, so these circles are in this direction according to the right hand rule. So according to the right hand rule, you will hold the wire with your right hand. Your thumb will point to the direction of the current, so your fingers will show you where is the direction of the flux. So there will be flux lines around the wire, and these flux lines are going up in this direction and going down in this direction. So if we look at the wire, here is the wire. So on the right side here of the wire, we have two flux lines. We have the original flux lines going down, and we have the generated flux lines going down too. And on the left hand side, we have the original flux lines going down, but the generated flux lines are going up. And you know that the flux lines are not intersecting, which means that these flux lines will cancel these flux lines, which will leave a weak flux on this side. So this flux here will be weak flux. So the flux here will be weak. So we have a weak field on the left, and we have a strong field on the right. So the strong field will move the wire towards the weak field. So the wire will move in this direction. And think about the flux lines. If you have an elastic and you started to stretch the elastic, if you stretch the elastic will give you force. And this force, you are stretching the elastic on both sides of the wire. Okay, so the wire is going here. Here is the wire. And these are the flux. So the flux will bend, so the generated flux can go here inside. This is the generated flux. So stretching the flux lines will create the force which will try to get the wire outside the flux lines. So the flux lines go back to its original situation where it was just vertical lines. And this movement will occur from the strong to the weak. That's why it will move to the left. And this is how they how they came up with their left hand rule. So they said if the flux is going down, the current is going in this direction, this will be the direction of the force. So this is I, this is phi, and this is the force. And if the current changes the direction, the force will change the direction. And this is how they came up with the left hand rule. So this is what is called the motor action, and the motor action is how you can generate force. Now let's go to the second type of action, and it is not surprise to be a generator action. So what is a generator action is? Okay. So the generator action is to produce EMF, electromotive force. We studied this equation E equal to BLV sine theta. So theta is the angle between the flux and movement. So assume this theta will be maximum. So E is the induced or generated EMF. So you have a generator because you are producing a voltage E. The main components you need to produce voltage V is you need flux, you need wire or conductor, and you need this wire to move with velocity V. So you need movement, okay? Or you need a prime mover. So any generator will need a prime mover, something to move the wires. If you move a wire inside an electric field, you are generating electricity. And this is how you can generate electricity. You need to move a wire inside an electric field. That's it. So the three components you need to build a generator are flux, wire, and movement. So these are the three components that we need to have. So flux, a wire, and a movement. If you have the three components, the flux, the wire, and the movement, you are generating voltage. And this is these are the components in any generator. And if you have a steam power turbine or steam generator or steam power station, you are getting the movement from steam turbine. If you have a hydro generation unit, so you are getting the prime movement or the mechanical movement from the water flow, so it is hydro generation. If you have a wind turbine or wind generator, the generator is coupled with the wind turbine, so you can get the prime movement or you can get the mechanical movement. So simply to build a generator, what you need a flux or field, source of field, and you need wire with length L, and you need to move this with velocity V. So if we start to say, you will assume that we have, this is a plane we have, and here is the wire, and this wire is subjected to flux, so the flux is vertical going into the paper here. So this is the paper, okay, and on this paper we have the wire and the flux is vertical. This is the flux. Now if you moved this wire with a force, so this force is an input force, and this input force or this mechanical force will be coming from a prime mover. So if you are moving this wire in this direction, you are generating electricity or generating E according to the equation BLV sine theta. And the direction of this E follows the right hand rule. So let's bring my right hand. So it follows the right hand rule. So for the right hand rule, you receive the flux into your hand. Your thumb points to the direction of the force. Your fingers will point to the direction of generated E. So generated E will be in this direction, which means here is negative and here is positive. So according to the right hand rule, so I will bring this one here. And I will rotate it. So the flux is coming into your hand, flux. The force is going in this direction to your right. So the EMF will be in this direction, which means we will have negative and positive E here. And the value for this E is BLV sine theta. And this is called generator action. Okay? And this is called the generator action. So to summarize, if you have a flux, wire, and there is a current going into this wire, you are generating a force. If you have flux, wire, and this wire is moving, you are generating voltage. Okay? So these are the two basic rules of electromagnetic. So wire moving, cutting flux, generating voltage. Flux and wire carrying current, generating force. That's it. So these are the two basic rules for the motor action and for the generator action. Now we will come back to a very important point. If we go back here, now although this is a motor action, but the generator action is there, okay? Why the generator action is there? Now you have a force moving the wire, and this wire will cut a flux. So if you have a force moving a wire and this wire is cutting the flux, you are generating a voltage. Where is the direction of the voltage? This is the right hand rule. So we need to bring the right hand to see what is happening here. So according to the right hand rule, this is the direction of the force. Flux is coming into your hand. So this will be the direction of E. So there is an induced E here, whereas here is negative, here is positive E. This is E induced. So here there is also a generated voltage E, and the well-known term for this E that we use, we call this E induced, is usually called back EMF. The back EMF or the reaction EMF. And this is what will happen in motors, okay? So again, we had a wire. This wire is subjected to flux. So we circulated current into this wire. So the wire will move. When the wire is moving, it will cut the flux, generating E. And this E is against I. And this is why the wire is moving, okay? So the idea, according to Newton's law, if you have a force, there is an opposing force equal in magnitude. So you injected current I, so there will be a reaction to this I. So you can add to Newton's law that if there is an action, there is a reaction from the same nature, which means if the action is mechanical, the reaction is mechanical. If the action is electrical, the reaction is electrical. So here you injected current I into the wire, so the reaction has to be electric. So the wire has to react to this current in an electrical reaction. And to get this electrical reaction, the wire will start to move to generate this E. And if you can see, this E is against the current. It consumes the energy from the current. So this E opposes I. So when you injected current into the wire, the reaction of the wire is generating a voltage against this current to stop this current from flowing. For the wire to generate voltage, it has to move. So you are getting the movement, or you are getting the motion from the motor as a byproduct. This is not the main product. The motor is trying to react to the current by generating a voltage, and to generate voltage, it moves, which is good, okay? We need it to move.